Okay, welcome back, lecture 4, video 2, and we are discussing feasibility of learning. Now, the question whether learning is feasible or not can be essentially split into the following two parts, right? There are two questions to answer. The first one is this, which tells us that can we make sure that this E out, which is the out of sample error, is close enough to the in sample error of G, of course, like for the final hypotheses that we selected, right? This is important because we are essentially trying to learn something outside of what we have, right? We are trying to answer a question for the entire universe of some problem, and we have a sample of that. So this is important, right? So feasibility of learning can be split into like two questions. The first one is, can we make sure that E out comes really close enough to E in, and of course of G, yeah, right? And the second question, again, equally important, is that can we make sure that this in sample error is small enough? Because that's all that we have, right? And this error is essentially telling us how much our hypothesis is really deviating from what could have been the target function within the sample, right? So we want it to be as small as possible because that's what our goal is. So can we make that? Can we make that? Can we make sure that the in-sample error is close enough or not? Now, if you remember from the previous video, we said that we derived this Hovding's inequality for the learning problem, right? And that Hovding's inequality that we derived before, it addresses the first question only, this one. Yes, we can make sure based on like whatever we got here, like there is this bound, and of course there are multiple variables in that bound, but depending on the values of the variables in the bound, we can somehow ensure that E in comes close enough to E out, right? So that was there. The Hovding's inequality will help us answer the very first question. The second question though, this one here, right, can be answered only when we run the learning algorithm on the data that we have and then see how small my in-sample error can get, right? So it depends on my data D. Okay, so with these two questions, what we realize is that there are many different components that can play different roles in the learning problem as a whole, right? And one such important component, and we'll keep talking about it like throughout as we dig deeper into the learning problem, is that like this complexity is really important, right? Now, again, as I said, there are multiple components in the learning problem, and then two of the important complexities that we really care about are the hypothesis set H, and to be very specific, we are talking about the cardinality, like the number of hypotheses we have in the set, right? That is what complexity means for H, and F is how hard is it to learn this target function, right? Because this could be something really, really complex if you think about it. This could be modeling, or I wouldn't say modeling because this is the target function, right? So this could be representing something really complex, right? A very complex phenomena. So both of them contribute to what is known as complexity, and going forward, we'll talk more about it. But before we jump into talking about anything else, let's look a little bit into what the complexity of H means versus what the complexity of F means, and how is the Hovding's inequality impacted by that, because like essentially we are trying to answer this question, right? And then we'll see how the complexity impacts my E in. Okay, so what I wanted to do here is to kind of come up with two sort of sections and try to differentiate between the complexity of H and the complexity of F. And although like even before moving forward, both will contribute to my learning problem, but we'll just like try to understand how this like complexity of H impacts versus how complexity of F impacts. Okay, so just remember, like the complexity here means the number of the size of this, right? So the number of hypotheses that we have. Complexity here means how hard it is to learn F, right? How hard is F? So that's what complexity means for H, and this is for F. Now, if we go back and think about this question 1, can we make sure that E out is close enough to E in, right? If the answer to that question is yes, right, what we have to do is, if we go back to the bound here, look at the equation here, right? What we have to do is we have to keep this m in check, right? This m shouldn't get too big if you really want a yes to the first question, right? So that means like the complexity of h has to be in like some control, right? So if the answer to the question one, if the answer to the question is yes, right? Question one is yes, then that means we have to keep my m, the number of hypotheses, right? So I have to keep m in check, right? It shouldn't be too big, because if it becomes big, it loosens the bound, and then of course the complexity of h is well, like will go up, right? But then it is bad for my question one. We cannot ensure that E out is close enough to E in, right? So that is the impact of the complexity of h on my bound. Okay, if we say yes for question number two, okay, let me write it down. If we say yes to question number two, which is, what was question number two? Can we make E in small enough, right? And definitely depends on the learning algorithm and the data. If we say that yes, it means that M must be big, because we stand a better chance of getting a smaller E in as a result of the flexibility to choose, right? I have a bigger choice, right? You write it. I have like a bigger choice set, right? And so like I have the flexibility to choose, but then it comes with a price. And the price we pay is that the complexity of h goes up, right? So if there's a yes for question two, m goes up due to the flexibility, or due to the result of choice, right? So you have to pay the price of increased complexity. And although we haven't jumped to the exact impact of complexity, but we can tell it's not really good, because m goes up, that means it's bad for question one, right? So there is a trade-off that's happening here as a result of the complexity of h. Now, similar to that, let's think about the complexity of f, right? Now, if you think about the complexity of f, this is something unknown, first of all, right? And then I don't really see a direct impact on question one, right? Why? Okay, if I say a yes or a no to question one, just like there, right? I would say no direct impact, of course, no direct impact, because, okay, why is there a no direct impact? Because if you look at the Hövding's inequality, we don't have an explicit f there. I don't have it in my equation, right? So because not there in Hövding's inequality. Yeah, it's as simple as that. But when we start answering question two, you'll see this might get impacted. Okay. Question two, is E in small enough? Can we make E in small enough? Well, the quick answer to that question is, if F is complex, right, then basically like D, the data that I have, right, is a result of F only, right, is a result of F somehow, because I got the data from somewhere, right? So if F is complex, then data from a harder F is difficult to fit, making E in worse, right? So the complexity of F, like if F is complex, E in will go up. Why? Because it is going to be a harder target function. It's going to be difficult to learn. No matter what I do, E in is going to get worse, right? So to get a better fit, now this is the inverse side of that. So I know that my E in is getting worse because F is complex. Now to get a better fit, what I'll do is I'll have to keep making my hypothesis set bigger, right? The more the choice, the better I am. Like I'm in a better position, right? Which means this is bad for question one, right? So yeah, it's not directly impacting question one, but as you just saw, that again, that trade-off exists even with the complexity of F, because indirectly, what I'll have to do is to improve E in, I'll have to do something, and that something is to go and like expand my hypothesis set, right? And the moment I do that, it's bad for my question one, right? So you can understand how the complexity of H and the complexity of F is overall impacting my learning problem. And also you can see, because like the feasibility of learning totally depends on these two questions. And there are two important or major players, I would say, the complexity of H and F, that are impacting like my feasibility of learning. And as I said, this complexity will play a larger role when we actually start selecting the hypotheses that we're going to see in the next video. But it's important to understand that there is a trade-off, and we as machine learning practitioners have this role to sort of come up with the best solution based on this trade-off. Okay, so what I'll do is, with this, I'll end this video. In the next video, what we are going to do is we are going to interpret the Hovding's bound and see how this complexity comes into play in a more sort of visual way, right? Thank you.